Welcome back, everybody. I think today should be a short day. Which is probably good for giving you time to get some of that verifying of identities done. I was watching Jordan and Davis and Keith working on some of the problems in the My Math Lab. It prompts you for some of the steps. You might also want to practice some of those problems without prompts of what those steps are, because you will not have those prompts on the test, and there will be verify one trig, at least generally one. Trig identity problem on the test, so. Don't just rely on the prompts, practice doing it without the prompts. Yeah,
Well, on the test, we have to verify and determine if a thing is false, or will they always be
didn't
verified?
you ask this question last week? Do you recall what I told you last week? No, I'm not gonna give you an equation that's wrong. Because it's really easy to verify it's false by fucking up. You can get every problem wrong by fucking up. And show that it doesn't work. It's much harder to show that it does work. And it doesn't help, it's not productive. For why we're doing this, you remember, in the future, you're not gonna see the other side of the equation. You're trying to rewrite something in terms of something that's much easier to use. We've seen some in those verifying trig identities, there's some really complex shit. When you're doing calculus on it, you're not gonna like that. But if you can do some manipulation and it all boils down to sine theta. That shit's easy. That's just golden to work on. You like if you can get anything down to something in calculus, down to something like sine theta or cosine theta, it's a fucking easy problem. You'd be surprised how easy it is. So that's why you're doing it, and you don't have prompts like that in real life. So and that's why having you prove something doesn't work, it's not productive to what we're trying to give you tools to be able to do stuff better later on as well. And getting the wrong thing isn't a tool. And you would never know. Think about this, if you had to prove something didn't work. You would never know if you just didn't go far enough. You're like, maybe if I did some more fiddling, I could get it. So like, yeah, it's. Alright. So, what is this, map 54? We are doing 7.3. This is on sum and difference formulas. And these ones are really important. They are really helpful. As are the 7.4 ones, at least half the 7.4 ones. We're not doing 7.4 today, 7.4 is on double angles and half angles. And the half that's good is surprisingly not the part that's called half angles. Alright. Let's start with cosine. If I have two angles, A plus B. And I do cosine of A plus B. This equals cosine A cosine B. And then I'm gonna pull out my trusty red pen and say minus sine A sine B. So maybe I'll use plus red over here for this. Because when we do minus. It equals the same thing, but with a different sign. Let's start with an example we should be able to do. One where we know the answer already. What is cosine of 135 degrees? They got that unit circle from your memory. You all did surprisingly well on that section on the test. What? Negative root 2 of 2. Some people ace the fucking unit circle and then like tanked the other half, including some, like the first question on the test, part B was like. What is this, give me all the trig functions for an angle that showed up on the unit circle, and people missed it, I was like, what, how the fuck did you do part A? And not get the first question, but it happens. I can rewrite this as. Cosine of 90 plus 45. Which means we should get negative root 2 over 2 when we're done, all is said and done. So we're gonna do, this is like A and this is like B. We're gonna have cosine of 90 degrees, cosine of 45 degrees. And then we do the opposite sign is minus. Sine of 90 degrees. Sine of 45 degrees. Alright. So what is cosine of 90 degrees? 0. What is cosine of 45 degrees? And then we got minus sine of 90. 1. Sine of 45 is root 2. And you'll see the first part goes away and we end up with negative root 2 over 2, just like we got. It doesn't seem all that productive to use it on things we already know though. But it can help us with other ones that are. Generally on things that are multiples of 15 degrees but are not on the unit circle. So like, could we figure out sine of 15? Oh, wait, cosine of 15. I haven't given you the sine formula yet. Cosine of 15 degrees. Can I rewrite that as something I know? A summary difference.
Minus 45.
60 minus 45 will work. You could have done 45 minus 30, but 60 minus 45 also works. And so this is gonna be cosine 60. Cosine 45. Plus. Sine 60, sine 45. What is cosine of 60?
1/2.
1/2. Lydia's getting faster. That's a good thing. What's root 2 shit,
Retorted.
right? We already said it. We've seen, got cosine sign written up above. What is sine of 60? Root 3 over 2. And we already did sine of 45. So it looks like I've got root 2 over 4 plus root 6 over 4. We could put together as 1. And if we need a decimal answer, we can get 1, but that's the exact answer. give you guys one to try. Cosine of 11 pi over 12. Well, this is a little tougher. I don't know, I just made that up, let me make sure I can actually do that. Yeah, you can do that. You might find it easier to shift that to degrees. While you figure out. What angles will add or subtract to it. Cause it's harder to think of the degrees that angles you've learned. In radians with a base of 12. Without converting all to 12, but it's easier, like I shifted the degrees here to make sure that this is doable.
I was gonna say, is there an equation we learned later that kind of allows us, it's kind of, it's almost like a quadratic formula that allows us to take really ugly equations and turn them.
We will do stuff that has quadratic formula with it, but it's not in terms of the angles. It's in terms of the functions themselves.
But I mean, I'm like, I think it'd be more like, they could give us a degree count. Just three. But that's not. But something where we won't need as much information to get it.
Well, the trig identities help you, doing the like the verifying identities help it where you don't need as much information. Like you can always, there's a lot of times to be able to manipulate stuff and rewrite stuff and things, terms of things, you know.
It's not, I was thinking it's like, I would be able to put 975. 1,007.
Yeah, there's no shortcut, that's calculated.
It's just come. Yeah, that is not easy.
Have you finished this problem, Davis? Stay on target. What is that in degrees? First off, make sure everyone's on the same page.
65.
It's 165 degrees. Did anyone get a combination that works?
And 145.
120 and 45 is a pretty good combo. So that's like 2 pi over 3 plus pi over 4. So cosine 2 pi over 3. Cosine pi over 4. Minus, we do the opposite sign for the cosine function. And cosine of 2 pi over 3 or 120 is
Yeah, one.
negative 1/2. Cosine of pi over 4,
Two.
root 2 over 2. Then I got minus sign, sine of 2 pi over 3. root 3/2. And we've got that. Oh.
4.
I'm getting ahead of myself. This is gonna simplify to negative root 2 plus root or minus root 6. All over 4. And we can get a decimal if we wanted, but. Let's give you one more. Cosine of negative 75 degrees. What is this madness? Negative. Wake up, Davis. Yeah, I see. Lock my eyes. What could I rewrite this as? What angle should I use? Let's make sure everybody's on the same page. Or at least a page that works.
I did negative 30 minus 45.
Negative 30 and negative 45 works.
No, just minus 45. Just like.
Yeah.
Yeah.
You can either do minus 45 like that or treat it as negative 30 plus negative 45. Both work depending on which formula you want to use.
Yeah. I used the first one you mentioned. Minus 45.
Okay.
Yeah.
So if we do the bottom one. Now, if you don't remember how the negative ones work. Can we use the odd and even function to make this a little bit easier? What's another way of writing cosine of negative 30 degrees? This is odd or even? It's even, which means we can rewrite that without the negative sign inside, because it's even. And what about sine of negative 30? Is sine odd or even? Sine is odd, which means we can pull the negative outside. Because it's odd. And now you know those work. What's cosine of 30?
2.
And we saw that one before. Sine of 30. So we got √6 minus √2 over 4 this time. And there's another way we can use this type of formula. What if we had cosine of 173 degrees? Cosine of 83 degrees. Plus sine of 173 degrees. Sine of 83 degrees. Now this feels like this is calculator hell. But what formula does that look like?
Cosine squared equals 1.
I would say yes if they have the same angle, but they don't have the same angle. How about I do that? Yeah,
Isn't it just cosine over 90? I mean cosine of 90.
how do you get that?
So-
Yeah, this looks like this function, right? And since it looks like that function, we can take advantage of that. This looks like cosine of A minus B. And this would be A and this would be B. So cosine of A minus B is 173 minus 83. Is cosine of 90 degrees, which is 0. Now, having done cosine A plus B and cosine A minus B, what would you think would be the next topic?
Squared.
You would think sine. We've done cosine, you would think sine would be the next thing. No, that's not what they did in the book. For some reason, the book does co-function identities first. We're gonna take a look at them. They can help. And I'm not sure why they prompted this. Maybe because they used it as, I don't know if they used it as a way to shift over to sine. But co-function identities do this. They're related, like we can do cosine of 90 degrees minus theta. And that will equal sine of theta. Sine of 90 degrees minus theta is cosine of theta. I gotta tell you, this is I have the hardest time memorizing these ones, and I don't know why. You'll see there's a very simple fucking pattern. But for some reason, my brain, my little peanut of a brain just will not wrap my head around these. Then we can look at tangent. Tangent of 90 degrees minus theta. And cotangent of 90 degrees minus theta. These equal the other function. And we get the same thing working with secant and cosecant. And obviously you can write these with either 90 degrees or pi/2 inside. You want it in radians? And they will give you problems like this. Yeah, I'm not sure how helpful this is. Secant theta equals cosecant of 62 degrees. So how can we use this? I wish I hadn't used theta there. Well, the formula is secant of 90 minus theta equals cosecant. So I can say, keeping that in mind, I can go, well, if this theta, like I can take advantage of this and go, what was this? We gotta do 90 minus 62 degrees would give me theta, which is 28 degrees. So I guess I didn't give the goal, find theta. We go with tangent x equals cotangent of negative 54 degrees. I guess find the missing angle, it's a better way to do it, since I changed letters here. So I could write this as tangent of 90 minus theta equals cotangent of theta. So we have tangent of 90 degrees minus negative 54 degrees has to equal cotangent of negative 54 degrees. And that means this angle here is 144 degrees. I'll give you guys one to try. Cosine x equals sine of 7 pi over 6. Alright, so what can I do here?
Can you subtract pi halves minus 7 pi over 6?
Take a look, the formula is pi over two minus theta. Equals sine theta. So if I do what we have here, we got pi over two minus theta. Equals 7 pi over 6. And I can add theta to both sides. And subtract 7 pi over 6. And I think that's what you said. I think you said pi over two minus 7 pi over 6.
Yes.
Looks like that's what we can do to find theta. What do we gotta do to make this happen? Common denominator, looks like I need to have a 6, which means multiply that on by 3. Which means 3 there. So theta is 3 pi minus 7 pi over 6. Negative 4 pi over 6. Or negative 2 pi over 3. And if we wanted to see what this angle inside here would be, what x would be. We would have pi over 2 minus that negative 2 pi over 3. So 3 pi over 6, I'm getting a common denominator here. Three pi over 6 plus 4 pi over 6, why am I getting 7 pi over 6 again? That shouldn't be right. Well, theta. I got that, what happened here? That is not the right theta. Cause theta here should be that one right there.
I mean, you already solved the cosine.
Yeah, I think it's just good, I think that's the one we wanted.
Yeah, that would be
Yeah.
one, yeah.
Yeah. Cause this is. Right there. Which is 210. And that would be the same as. That's a negative value on sine, so cosine having a negative value of that. Is the 60 degree reference angle. Or 120, which is 2 pi over 3. Wait, negative 2 pi over 3. There we go. That's what's fucking me up. Alright, so that was right. Alright, so. Now that we're done with that lame shit. Did anyone like the cofunction identities? Let's get to our sign of A plus B. I'm gonna use red again to distinguish the difference. And I'm just gonna write the formulas without the signs in there. We have sine A cosine B on both of them. And then we have sine B cosine A on both of them. And if we do plus. We get plus. We do minus. We get minus. So cosine swap side. Swap plus to minus and minus to plus. Signs keep the same.
So Professor Jones, if there's a negative on the inside of the parentheses, which ones would we use?
A negative is a negative,
Oh, okay.
like I wrote it. You're fucking with me, aren't you, Keith?
I was thinking about cosine. Sorry.
Oh, cosine, we already did cosine, maybe you missed the beginning. I didn't hear you talking in the beginning, so you might have showed up late, those were the cosine formulas.
Right. Oh, okay, okay. All right.
See, they swap signs. Negative goes to plus, plus goes to minus, but sign keeps them the same. Fuck it, let's write down tangents while we're at it. Tangent of A plus B. In fact, I'll use red again to show signs again. This will give us tangent of A plus B on top. Fraction, what? Tangent's the worst. One minus tangent A, tangent B. And tangent of A minus B. This is really like doing plus the negative B. You'll get tangent A minus tangent B. Over one plus tangent A tangent B. Now, as you're going down the math road and engineering road, I want to say the tangent ones show up less than cosine and sine. Cosine sine shows up a mediocre amount in these sum and difference formulas. Tangent less. But they do show up. So let's do some problems with these. Let's find sine of negative 15 degrees. What two angles can I use to get negative 15?
35 plus 30.
We could do negative 45 plus 30. So this is an A plus B. So we do sine of one, cosine of the other. And then we keep the plus sign and then we swap them. Sine of 30, cosine of negative 45. If you're comfortable working with the negative degrees, you can save yourself a step. But if you're not, using the odd and even identities will help. Sine is odd, so this becomes negative sine of 45 degrees. Cosine of 30. And I've got sine of 30 degrees. Cosine is even. So negative 45 is the same as positive 45. And we've beaten these 45 degrees to a pulp. This is negative root 2 over 2. What was cosine of 30? Root 3 over 2. Sine of 30 is. And 45 was root 2 over 2. So we get negative root 6 plus root 2 over 4. What about tangent of 13 pi over 12? So it might help shifting this to degrees. I believe we get 195 degrees. Can I write that in terms of the angles I know? $150 plus 45. There's a lot of ways we could have done this. 150 plus 45. You could have done 135 plus 60. But Lydia bust out with 150 plus 45, so that's what we'll go with. I'm gonna shift that back into radians though. Just because I can make you think about that in radians. There's a reason for it. We use calculus, we use radians way more than degrees because radians are better. You'll see why. I don't know if I've shown you why. I think I did. I think I showed you the derivative of sines and cosines in terms of degrees and radians. And derivative of sines is cosine in radians, but if you have it in degrees, you have a 180 over pi that you gotta remember to put in there. You won't remember that. It's fucking miserable. So this is the tangent one. This is gonna be, we do the same sign on top. So tangent of 5 pi over 4 plus, not 5 pi over 4, 5 pi over 6, let it be mixing shit up. Over tangent of pi over 4, and then we've got 1 minus tangent of 5 pi over 6 times tangent of pi over 4. And if you wanna work with degrees to figure out what shit's going on, feel free to. Tangent of 150 is sine of 150 over cosine of 150. What is sine of 150? Or sine of 5 pi over 6? It's 1/2. Which means this one's gotta be the root 3 over 2, but we are in quadrant 2, so it's negative. That ends up being negative 1 over root 3. Or negative root 3 over 3. So that's the tangent part. So I've got negative root 3 over 3. What's tangent of pi over 4? 1. Hopefully the ones in quadrant 4 or quadrant 1 are a little bit easier to remember. Then we've got 1 minus negative root 3 over 3 times 1. So we end up with 1 plus, nope, 1 minus root 3 over 3 over 1 plus root 3 over 3. And I'm not a big fan of complex fractions, so what we're gonna do is multiply that by 3 over 3. And you will get 3 minus root 3 over 3 plus root 3. And if we wanted to like do it properly. Get rid of the radicals on bottom, we could. By multiplying by the top and bottom by the conjugate of the bottom. That's some more algebra though. You'll get 3 minus root 3 squared on top. On bottom, you get 9 minus 3 over 9 minus 3 is 6. That's an a squared minus b squared. A plus b, a minus b is a squared minus b squared. If we apply this to this, 3 squared minus root 3 squared. 9 minus 3. So this is probably the way the computer would take it. For me, if you got to this point right here. You definitely don't want complex fractions. At least get to that point right there, like on the test. And then if you did like the actual thing, I might be pleased and give you a bonus one. Let's take a 10-minute break.